The next one is also about DETR. It's an extension of it. DETR is a very nice method because unlike the type of methods that were based on CNNs, here you are getting rid of a lot of handcrafted components. And what do I mean? For CNN-based architectures, you were doing anchor generation. Some of them were anchor-based, some of them were not anchor-based. But whatever that you do, you're gonna say that this object in my ground truth is gonna correspond to this anchor. And then the way that you were assigning them was kind of ad hoc. It was rule-based. You were saying that if my intersection over union, or if the intersection over union between an anchor or a box proposed or a proposal box and the ground truth is bigger than a threshold, that's a positive example. And the question was, what is that threshold? How are you setting it? So these are a lot of hyperparameters. The other one is you do non-maximum suppression at the end, which DETR doesn't need it. So it has a lot of benefits, but it also has nothing is for free. It has its own downsides. We know that attention mechanism is expensive. It's going to have a quadratic cost because each element in your set needs to pay attention to every single other element in your set, and that's expensive. It has quadratic cost, and it's a limiting factor. Why is it limiting? Based on your target device and the capacity of your hardware, you're going to need to work with lower resolution images so that you don't end up with inputs to your transformer or sequences to your transformer that are really long. That's a limiting factor. The other one is usually these attention mechanisms, unlike convolutions, are going to take a long time to converge. They're slow learners. And why is that? Because they need to start from scratch. There is no bias in them. And each element is equally likely to pay attention to every single other element in your set. This is unlike CNNs that you have a local neighborhood and you are paying attention to your neighbors. So there is some inductive bias in CNNs that is absent from transformers. And this paper is trying to mitigate these two issues. How is that? The idea is if I give you a budget of 3 neighbors or 4 neighbors or 5 neighbors to pay attention to, which 4 neighbors are you going to pay attention? And can you do that in an automatic fashion? So that's the idea. The idea is using deformable attention module. And these ideas of deformable we saw before when we were considering deformable convolutions. And I think as soon as I show you a little bit of the math, you're going to draw the connections with deformable convolutions. So first of all, we usually look at feature maps at multiple scales, which could come from feature pyramid network type of ideas, or they could come from multiple images at multiple scales, a pyramid of images. So you can have multiple feature maps coming out of the first few layers, which are convolutional. We saw in the DETR architecture, the first few layers are convolutional. For the rest of this, we can assume, and this figure here, you can assume L is 1 because you can generalize this. So it's going to make our lives much easier. So L is 1. You're going to have a feature vector for a query element because for your attention mechanisms, you have query key value, and the query is going to pay attention to the keys. It's going to give you some attention weights that you're going to spread among your values. So you're going to pick a query, and this query could be one element, one pixel of this input feature map when it comes to encoder. So ZQ is exactly one pixel there. Or when it comes to decoder, if I go back here, when it comes to decoder, it could be these object queries, which are just positional encoding vectors. So that's your Z. And this is this part of the figure. And X is here, which is your input feature map. There is one other thing, is the location of this pixel. Which pixel are you taking? And these are the normalized coordinates so that they have a value from 0 to 1. So you're scaling it according to the scale of your feature map at that layer. And these are 2D coordinates, the X location and the Y coordinates. So far, so good. Now the question is, if you have a budget of three neighbors to pay attention to, among all of these pixels, which ones are you going to pay attention? You are not allowed to pay attention to everybody. You're allowed to only pay attention to 3 neighbors. Which ones are you going to pay attention to? This is this figure in math. We said we are going to assume L is 1 So you're not going to look at multiple scales. It's easy to generalize that. We don't need to work with multiple heads. If you understand one head, you're going to explain multiple heads. So we're going to look at only one of these heads. You're going to have some attention weights. We got rid of M, L. It's how much you're paying attention to each one of your neighbors. So K is going to count the keys. So how much attention are you going to pay to this location, to this other location, and to the other location? And they're going to add up to 1. And these are coming out of your attention weights. And then you're going to do your aggregation, put a single vector here. It's the average of these 3 vectors according to these attention. And mathematically speaking, it's the same thing. So this is doing the averaging for us. It's a weighted average. These are for multiple heads. We don't need to worry about them. X, L, we set it to be 1. We don't need to worry about it. And PQ is the location here. And phi is just adjusting it because you might have different scales. You're translating a pixel location from one feature map to another feature map in another layer of your convolutional neural network. So this is just going to adjust those locations. We assumed L is 1, so we don't need to worry about it. The only thing that we need to worry about are these offsets. Where are you going to pay attention to? I know that you are sitting here. What are your deltas? And those deltas are going to be, in this case, 3 two-dimensional vectors. And you're operating at the pixel level. The problem is these locations might end up not on your grid. To fix that, you're going to do interpolation. What are the benefits? Usually, K is a hyperparameter that you're going to choose. You're going to choose it much less than your resolution. If NQ is the number of queries, the number of ZQs that you have, which could be different if you're at the decoder level or at the encoder level. At the decoder level, NQ is H times W. At the decoder level, it's the number of predictions that you want to make. This is the total complexity, computational complexity. For only one L, you can extend it to have multiple Ls, multiple scales. When it comes to the encoder, NQ is H times W because each pixel is going to pay attention to every other pixel. And the cost is now linear. You don't have these square terms anymore. And when it comes to the decoder, you're going to depend on the number of outputs that you have and a hyperparameter, which is totally under your control. So this is no longer quadratic in the cost. You're going to report some good results comparable to faster or CNN with feature pyramid network with DETR. You can have iterative box refinement type of ideas that we saw before, but nothing is for free. This is beautiful, but when you actually implement this might end up being much slower than you expected. Why? Because modern hardwares like CPUs, TPUs, or even our CPUs, they like to access the memory in an ordered fashion. This is unordered, and this could end up being slower than you expect it to be. I think it's a good time for me to stop here. For those of you who have questions, I'll be around.